name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing. Hi, and welcome to the 7th talk in the ITS RF Spectrum Measurement Seminar Series. Up to this point in the series, we've put together a set of building blocks that relate to the way that spectrum measurement systems work, and in the most recent talk, the way that radars work. And the reason we've been doing this is because we want to build up to understanding how to measure radar emission spectra. The talk today is on the topic of the difficulty of measuring radar emission spectra. And today I'm not going to give the solution to the problems, but I am going to explain what the problems are. And the way that I want to introduce this is by first of all explaining why we particularly in NTIA, in the U.S. Department of Commerce at least, want to be able to measure radar emissions at all. So I'm going to start off with a radar spectrum engineering criteria, RSEC, spectrum emission mask, a description of the mask, showing what it is that NTIA says radars need to meet as an emission criterion in the spectrum. And then, with that mask in place, I'll explain the problems of trying to measure radar emissions for compliance with the mask in terms of 3 particular problems. That, first of all, conventional swept spectrum measurement systems like spectrum analyzers that sweep their way across the spectrum, have a relatively low probability of intercepting radar signals, and therefore it's difficult to fill in a radar spectrum with a swept frequency system. Second of all, that we have a limited amount of instantaneous dynamic range in these measurement systems. And I'll preface that with, there are ways to extend the dynamic range of the measurement system, but if we start off with an off-the-shelf spectrum analyzer, we are limited on dynamic range. And in fact, that this dynamic range is not enough to show compliance with the RSEC. And then thirdly, I'm going to show an even deeper and yet more subtle problem, which is that the radar spectra that we measure vary as a function of the bandwidth that we use to measure them. We look at an emitter and we think the emitter has a spectrum. It has an emission spectrum, and we can see that emission spectrum by doing a Fourier transform of its time waveform. The problem is that any real spectrum has to be measured in some measurement bandwidth, and we've seen this in the previous talks. And as we change the measurement bandwidth, I'll show you with a lab session today with a radar that we're generating in a vector signal generator, that in fact we don't get the same spectrum from one measurement bandwidth to the next. And so the problem that we'll be left with today is how do we solve this problem of low probability of intercept and limited dynamic range, and the fact that we get an answer to our spectrum measurement problem that varies as a function of the bandwidth we pick, and yet we're trying to fit the spectrum under one particular emission mask. So, with that said, we've still got our last talk left over. Take care of that. With that said, I'll lead into the RSEC. Now, NTIA, as an agency, seeks to promote electromagnetic compatibility. Compatibility between radio systems. And for our purposes today, this means, for example, from a radar to a radar, and from a radar to a comm link, communications link, etc. And we recognize that absolute compatibility is generally not possible, but we try to make systems as compatible with each other as possible. And in terms of pursuing that compatibility between systems, NTIA has developed the so-called Redbook, the Manual of Regulations and Procedures for Federal Radio Frequency Management. This book is available online at the NTIA website, ntia.doc.gov, and specifically there's a sublink for the Office of Spectrum Management where I believe you can currently find this book. And this book is very much of an engineering manual. It is in the form of a binder so that physically we can update it whenever we need to, and of course the version that's online is always up to date. And among the many things that we find in the book is chapter 5 on spectrum standards, and inside chapter 5 is a section that describes a particular set of standards that radar emitters are supposed to meet in order to try to achieve some kind of electromagnetic compatibility between radars and other radars and comlinks, etc. And that standard is called the Radar Spectrum Engineering Criteria, the RSEC. And you notice that we use the word criteria plural. There are actually several criteria. The criteria include a spectrum mask, antenna pattern behavior, local oscillator radiation, although that one may get dropped in the near future, and etc. But on the basis of past history, what we found is the most important single one of these criteria is the spectrum mask. We want the radar spectrum emissions to fit within a particular mask that we can draw in the spectrum. That's the most critical of all. There are a variety of other criteria described here in the Redbook, and you can always download Chapter 5 and go through those. But this is the most critical of all. So, what does this mask look like? The concept of the mask is what I'll give first. Imagining that a radar has an emission spectrum which looks like this. Here's power, here's frequency, and imagining that we have a radar with an emission that looks like this. It's emission spectrum. And that's not a bad representation for what some radars might look like. And by the way, bearing in mind that the classical sin x over x squared spectrum that consists of a set of lobes is right up in here in this central part of the spectrum, and that these parts of the spectrum that we see coming out of the sin x over x squared, the so-called sinc squared part of the spectrum, are emissions that are primarily due to the behavior of the high power output component that the radar is using. For example, a magnetron or a klystron or a solid state transmitter of some sort. NTIA draws a mask which looks like this. First, there's a chimney which goes from the 0 dB point in the spectrum, 0 dBc actually. Remember, decibels are equal to the power at the center frequency. We start off at 0 dBc, like so. We draw this out to a certain width. I'll give you the width in a moment. And we drop this by 10, 20, 30, 40 dB down. So here's a point that is 40 dB down. Let me write this slightly. There we go, minus 40 dB down. Now this does not have to be centered. This doesn't. Doesn't have to be centered. Interestingly enough, at the radar's center frequency. So you can slide it back and forth, but conventionally we just draw it centered on the radar center frequency. And then, from this point down, we draw a sloping line, and I'll describe the characteristics of this sloping line in a moment, which comes down like this, and it's symmetrical, like so. And this line continues down indefinitely, but we truncate it at a point which is at an ultimate suppression level called minus X dB. And typically X is equal to 60 dB down, but X can be equal to as much as 80 dB down. So this ultimate suppression level, right here, ultimate suppression level is a function of the type of radar that we're looking at. And the way that we finish off the mask is to draw this sloping line down like this until it hits that ultimate suppression level, which is defined in, again, the Redbook for the type of radar that you're working with. And then at that point, we draw the mask out like this at that ultimate suppression level, and the mask is drawn out indefinitely on either side of that. And this line, although it's a little hard to tell from the way that I have drawn it, is in fact a curve. This is not a straight line. This is a curved line that rolls off down to the ultimate suppression level. And so, this mask leads naturally to the definition of some regions. Inside this 40 dB chimney, we can refer to these as in-band emissions, or we can call it the minus 40 dB emissions, like so. That's inside this section right here. Then, these two sectors, here and here, which I'm going to color in blue like this, like so, are referred to as out dash of dash band. Out of band. I'm going to erase this part down here. I'm going to make it a little more obvious what I'm doing. So out of band and out of band. These are the so-called out-of-band emissions, this part of the spectrum right in here, where we're rolling down from the minus 40 point to the ultimate suppression point, minus X. And then the rest of the spectrum, which I'll color in green, like this, is spurious. Now, nature doesn't give us in-band, out-of-band, and spurious. We make that up ourselves. But it is a useful, we found it to be an NTIA, a useful engineering reference that we can use. That's about it. And collectively, by the way, the out-of-band and spurious emissions together, so all of these emissions and all of these emissions, in other words, all of the spectrum emissions except for the so-called in-band emissions are also referred to as unwanted emissions. So if we want to, we can lump the out-of-band and spurious together as unwanted emissions. So this gives basically a map to radar emission spectra, and this is how the RSEC curve is drawn. And I will, in fact, write this as RSEC mask. RSEC mask. Like so. And I do emphasize that these ultimate suppression level parts of the mask go off to plus and minus infinity in the spectrum domain. So, it seems simple enough. We say, okay, here's this mask. We draw it like this. I do want to give you a couple of details here on the mask. First of all, the 40 dB bandwidth, this bandwidth right here, for the 40 dB part of the spectrum, which is written this way, B minus 40, is for a simple pulsed radar. That is a radar which transmits pulses with some pulse width t, tau, which have some little short, usually a short rise time, t sub r, is 7.6 divided by the square root of the rise time multiplied by the pulse width tau, where the units of the 40 dB bandwidth are megahertz, and the units of t sub r and tau are microseconds. And this part of the emission mask, along with the roll-off and emission mask, is based on a theoretical analysis of what a radar emission spectra should look like, given that the radar puts out pulses with certain pulse widths and certain rise times, which are assumed to have envelopes which look like this. Here's the RF. Here it is turning off. So the pulse is assumed to have a trapezoidal envelope that has a rise time, this is the time domain, a rise time, a pulse width tau, and a fall time. And the fall time is generally longer than the rise time. By the way, in this equation, if the fall time should be shorter than the rise time, then the fall time is used. It's whichever one is shorter. But assuming that the radar pulses have a trapezoidal envelope, such as I've drawn here, then the RSEC mask provides a reasonably good tool for the envelope within which the radar emissions ought to fit. Your bets are off if the radar pulses look like this, where the pulse envelope looks like that. And I have seen that happen. But the RSEC does not account for that. The RSEC was written with the assumption that radar pulses have that kind of a shape. Most radar pulses do, but there are some that are, I'll call pathological, that don't. Pathological radar cases, where what you have is something that looks like a rise time followed by a fall time, and where the pulse width is 0. And that doesn't work in this model. You need a different model for that. But the spectrum this produces is going to be a somewhat different spectrum anyway. Okay. One other thing to point out is that when we get to the 40 dB points in the spectrum, and we have to compute this roll-off, there are different possible roll-offs available. Instead of rolling off the way I've drawn it, we could make the mask roll off like that. We could make the mask do that. I'm going to draw it like this right here. I'm going to clean up this stuff in here to make it a little more obvious. Like so. In other words, we could say that the mask needs to come down at a steeper rate right here, down to that ultimate suppression point. And in fact, this roll-off rate, the roll-off rate, right now is equal to 20 dB of roll-off per, we say, decade. But we could make it roll off at a steeper rate. I'm going to go back over here, roll-off rate. Roll-off rate. Again, this is referring to how fast it drops right in here. Roll-off being how many dB down you go in a certain number of megahertz going across. The current roll-off rate is 20 dB per decade for most radars. Most radars. This does vary a little depending on the radar type. Other possibilities would be 30 dB per decade, 30 dB per decade, or even 40 dB per decade. And you say, wait, what do you mean dB per decade? I mean dB roll-off for every factor of 10 that you change frequency. And the equation for that is in the Redbook for actually computing it. You can type it into an Excel spreadsheet, for example, if you want to actually compute it. So every time you get 10 times further out from the fundamental in frequency than you were at some previous point, you're either down 20 dB or down 30 dB or down 40. Obviously, these represent tighter emission masks to meet. And at the time that I'm giving this talk, NTIA, working in concert with other agencies in the U.S. Interdepartment Radio Advisory Committee, is in fact discussing whether or not we need to move from 20 dB per decade to either 30 or 40 dB per decade for various types of radars. The bottom line is that the shape remains the same. It's just a question of how sharply we feel that we can roll that down. And this really depends upon how good we think these radars are that are operating as part of the spectrum. Julie?
Is all of this discussion just for primary radar and not secondary?
Correct. This is for primary radar. The question is all this discussion for primary radar only? The answer is yes. Primary radar being radar that fires RF pulses like this off into space and gets the echoes back. Secondary radar being beacons that are on aircraft. And no, so this does not apply to beacon emissions. This is a reference only to radars that are actually putting energy into space and getting reflected echoes back. Good question. Okay, so from the standpoint of today's talk, here's the important thing. The important thing to realize is that this whole argument has been couched in certain terms. It's been couched with an assumption that there exists a level at this frequency right here, for example. There exists a level of power that the radar emits, which can be measured a certain number of dB down relative to this power level, which the radar emits the fundamental. That's what that's the term. Those are the terms in which the mask is couched. Keep that in mind. It's going to be important later when we do the lab. He laughs diabolically. Any questions on that? I'll leave the center part of this picture up for the time being. I'm going to erase the parts around it right here because they're not terribly important. But this will allow me to segue into the next part of the talk. Okay. Now, let me write that DBC over here. Okay, so let me just slide through. Okay, so now we've configured the problem. So far, so good. The next part of the problem I can take care of on this part of the board. The radar emissions that we need to look at, as we saw in the last talk, are almost always running, I'll draw a line out here, at about 1/10 of 1% duty cycle. Meaning that the pulses that we see are on about 0.1% of the time that we have between pulses. For example, and we saw this when we did our air traffic control radar last time around, typically we're firing pulses that have a pulse width tau that's equal to about 1 microsecond. This is for a medium to long range air traffic control radar, with an interval of time until the next pulse occurs, which is in fact about 1 millisecond. 1 millisecond. 1 millisecond is 1,000 microseconds. So this radar is only on for 0.1% of the time, and to make the problem even more complicated, as we pointed out again last time, the radar emissions themselves are contained in an antenna beam, which looks kind of like this if we're looking at air traffic control radar seen from above. The beam contains something like 10, 15, or 20 pulses, like so, and this beam, which is rotating like this in space, might have anywhere from 1 second to maybe a 12 second, depending upon the radar type, rotation interval. So, first of all, the radar is only on 0.1% of the time, and second of all, the beam only looks in our direction about once a second to maybe once every 12 seconds, depending upon the radar type. And when it does look in our direction, given that we might have a millisecond between pulses and we might have 10 or 15 or 20 pulses in here, the beam itself is only going to last for a time interval that's something on the order of 10 to 20 milliseconds long. So we're only going to see a burst of about 10 pulses with a spacing of a millisecond between them every second, or maybe every 10 or 12 seconds. So you're sitting here waiting like this, and eventually you get a bloop. There were 10 or 20 pulses, and then you wait. 10 seconds goes by for long-range radar. Bloop. There it was again. And we're trying to get the spectrum measured on this thing, and it's hardly ever turned on, and when it is turned on, it's hardly ever looking at us. So this results in a really low probability of intercept in terms of seeing these signals. And this becomes problematic if we're trying to fill in a spectrum that's going to look like the one that I drew in black here, where this spectrum, when we're measuring it for compliance with the RSEC, might typically need to be measured over a range of several gigahertz or gigahertz. We've had radars where we had to measure across, I've certainly had to go 6 gigahertz on some radars, for example. And that's a lot of spectrum to have to measure across and try to fill in when the radar is in fact hardly ever looking at us. And I'll show you the exact problem when we do the lab here shortly. So what we need is a fast and efficient way of making that measurement. We need a fast and efficient way of getting ourselves through that spectrum. And we have a way, but I won't tell you what it is today. It'll be next week. So that takes care of that problem. It takes care of the explanation of that problem. That problem's explained. Now, next problem, dynamic range for the measurement system. Here's what we're up against. Here's what we're up against. Remember that depending upon the radar type, and the radar types are described in the Redbook, this ultimate suppression level X may equal either 60 dB down at a minimum to as much as 80 dB down for some types of radars. Now, if we want to measure a radar spectrum for compliance with a 60 dB suppression level, we might naively say, well, then we need to be able to measure at least 60 dB down. But I contend that no, we need to measure at least 10 dB more than that, because remember that if we have spectrum analyzer, or just doesn't have to be spectrum analyzer, if we have measurement system noise right here, here's frequency, here's power, here's our measurement system noise with no signal coming in whatsoever. We've got some level on the noise right here. We have a signal, and we're trying to measure the power in that signal, and we're measuring the signal spectrum like this, and we're measuring the signal down. As the signal comes down like this, we're going to see this happen. See what I drew right there? It's going to come down. I'll make the spectrum even steeper on this side. We're going to see a rollout like that. Now, why do we see it do this funny? We always see this. We always see this funny little rollout right in here. In other words, just when you think that it's about to plunge down into the noise like that, you see it rolling out instead. And the reason is, I'm sure, right, we're summing, I'm not sure if everybody heard that now, we're summing the spectrum analyzer noise power, which I'll write as P sub noise of the spectrum analyzer, with the power in the signal that we're trying to measure. So as we're getting close to the noise, and these two are summing themselves up. In fact, when the power in the signal that we're trying to measure is equal to the noise power of the spectrum analyzer, we're going to see the sum. And what do we see? We see power 3 dB above the spectrum analyzer's noise floor. We see power 3 dB above the spectrum analyzer's noise floor when the power we're measuring is equal to the spectrum analyzer's noise. there's nothing wrong with that. I mean, that's how the physics of the device need to work, as we saw in the section where I talked about how spectrum analyzers work. But if you're trying to just read off the spectrum, it's a problem. And go try to explain it to somebody who doesn't really understand it. They think you're trying to sell them a used car. You're telling me that what you measured is perfectly accurate, but it's 3 dB off from what it really. Okay, so don't do that. So here's a better way to do it. If you're trying to measure down to a limit like this, get the spectrum analyzer noise down in here like that, and then as you continue your spectrum measurement, what you can do is get rid of the noise here. Bring your here, I'll redraw this. Get your measurement system noise down in here like this. Then, by the time that you're getting into this zone where you get the roll-off going, you've already hit this ultimate suppression level of minus X dB, 10 dB up above the spectrum analyzer noise. So my contention is that to make it easy on yourself, so you don't have to do what I'm doing now to explain all this to somebody who doesn't necessarily really get it, just try to get your spectrum analyzer, your measurement system noise, another 10 dB down lower than the limit you're trying to measure to. But that means that if your ultimate suppression levels on the RSEC mask are 60 to 80 dB, you really need to try to get actually 70 dB to 90 dB of dynamic range available in your measurement. And if you can get even more than that, all the better. Remember, we're trying to promote electromagnetic spectrum compatibility with the NTIA measurements, so we're trying to do better than just measure down to the mask limit. We want to see as far down as we can possibly go. I take it as a personal challenge to get 100 dB of dynamic range in a measurement or bust. But that's just me. But to show compliance, you've got to get 70 to 90 dB. And so we have now the dynamic range problem where we need to get 70 to 90 dB of dynamic range, and we may not necessarily be able to get that. And again, we'll look at that on the spectrum analyzer here in a minute. Okay, so this is our problem outline. And now the last piece of the puzzle, which I'm going to draw on the board, but I'm going to show you, is the most subtle of all. The radar spectrum varies as a function of the bandwidth that we use to make the measurement. Now I'm going to go ahead and kind of erase this and redraw it. We'll get this back. I'll get it back in a moment. Now, I've already alluded to this in an earlier talk, so I'm not going to belabor the point unduly, but I do want to remind everyone of this because this is one of the more subtle parts of making a spectrum measurement. If we are looking at a pulse emitter, and we'll just, for the sake of simplicity, we'll make it a very simple pulse emitter, which is producing pulses which last for an interval tau each, time domain, and this is, you know, again, for many radars, it's a number that may be on the order of a microsecond. Although, as we saw again in the last talk I gave, these real numbers can be all over the place because every radar is a sort of a electromagnetic work of art, and pulse widths can vary widely. And if the time between the pulses is on the order of, say, 1 millisecond, between the pulses here, then we develop a radar emission spectrum that looks near the fundamental frequency F0, frequency, power. We get a spectrum which will be a line spectrum, and the lines will look like this, and so forth out. And I'm not going to draw all the lines all the way across, I'm just going to draw the envelope for the lines, like so, like this. And the spacing between any two of the lines will be equal to 1 over the pulse repetition interval, in this case 1 millisecond. So for example, in this case, for example, these lines would be spaced 1 kilohertz apart, because we're putting out 1,000 pulses per second and 1 millisecond between. And the null to null spacing on this spectrum will be equal to about 1 over the pulse width, 1 over tau, which would be, in this particular example, a megahertz. And the width of the center lobe is 2 times 1 over tau. So for this example, it would be 2 megahertz wide right here. So far, so good. And again, bear in mind that these are lines going all the way across through here, like so. And we already saw, and this is important, we already saw that if we are using a peak detector and we change our measurement bandwidth such that we change the number of lines, that the variation in power that we measure with the peak detector will go, that this power level that we measure will go as 20 log of the bandwidth in which we're making the measurement. So if you double the number of lines, you don't get 10 dB more power, which you would with noise, which consists of a lot of uncorrelated energy in the frequency domain. Instead, because these lines are phase correlated with each other, we get a 20 log relationship if we're peak detecting. If we're peak detecting, which we will be for a radar emission, because we're trying to see these little short pulses in time. So if we're peak detecting and we change our bandwidth by some factor, we're going to get a 20 log variation in the amount of power that we measure in this part of the spectrum. Now, as people have commented to me, this is a bit of an approximation, but it's a pretty good approximation. If we widen the bandwidth, we'll go up at the rate of 20 log. If we narrow the bandwidth, we'll go down at the rate of 20 log. So I'm going to draw a couple of separate spectra out here. This is the spectrum drawn in a wider band, the spectrum measured in a wider bandwidth out here. And then in green, here is what the spectrum out here will look like if we measure it in a narrower bandwidth like this, like so. And that variation, again, is going to go about 20 log. Now, I've done studies on this. We've published the studies. Sometimes you see about a 13 or 14 log variation. Sometimes you see a 16 log variation, you might see 20, but it's on the order of 20 log. The exact behavior depends upon the exact behavior of the shape of the radar spectrum out here. If this spectrum were perfectly flat and had no lobe characteristic at all, we should get an exact 20 log, but the spectrum does vary up and down. Now, however, what if we're making power measurements at the fundamental? Well, if we make a power measurement at the fundamental in a bandwidth which is narrower, here's our measurement bandwidth. Here's our, I'm going to draw B sub m. Here's our measurement bandwidth, B sub mes, right in here. We start off with some B sub mes, which is less than the width of this lobe, which for our example here is say 2 megahertz. So we start off with some B sub mes that's substantially less than about 1 over the pulse width. We measure some power level, and we can draw that power level over here like that. There we go. Then we widen our measurement bandwidth out until it about equals the width of this lobe right here. And when we do, we get a power level that measures out like that. And I'm going to, in fact, here, I'll color code this. I'll make this one green. There we go. Make this one green to show that this was the power level that we measured with this narrow bandwidth right here, where the power level in this part of the spectrum was down in here. There's our green. Then we come to the red, which is the power level that we measure in a bandwidth which is a matched filter bandwidth, which matches about 1 over the pulse width of the radar, in other words. We measure this power level right here. And then, here comes the tricky part, when we go to the third bandwidth, this wider bandwidth, where the power out here in the out-of-band part of the spectrum, and for that matter, out in the spurious part of the spectrum, so through all the unwanted emissions, is going up at 20 log of the bandwidth, what do we measure? The same value. The power stops going up at the fundamental when our measurement bandwidth equals or exceeds the width of that central lobe. Now, admittedly, there is a fraction of a dB more power, maybe a dB more power that we get as we widen ourselves out to this wider bandwidth that I've drawn in blue here, but not by much. Okay, wait a minute, there's a problem. We said that we wanted the spectrum emissions to fit underneath a mask that looks like this. And we said that we were going to measure power here, and we're going to get the spectrum out here under the mask like this. We want to see if it matches it. And what I've just done was to put together a scenario where if we measure in some bandwidth, we get the same power here in the second red bandwidth as we had in our first blue bandwidth, but where the spectrum emissions out here run out like that. And where, in other words, there's an offset in power. In other words, if I go to this wider bandwidth relative to this more narrow bandwidth, the offset in power at some frequency out here relative to the fundamental changes as a function of the bandwidth that I'm measuring in. So there is no single emission spectrum that the radar produces in terms of the way that we have to measure it. We have to measure it with some bandwidth, and we're getting a variation in here. Now it turns out that if I measure in more narrow bandwidths, as this drops 20 log, this power at the fundamental also drops 20 log. So if I'm measuring a bandwidth that is about equal to or less than 1 over the pulse width of the radar, I keep getting about the same offset between the power measured at the fundamental and the power out here. But if I go to a bandwidth that's overly wide, I wind up in a situation where I get no more power here in the wider bandwidth than I got in some narrower bandwidth, but where I do get a higher measured power level out here in this part of the spectrum. And the reason is that in this part of the spectrum, we're measuring almost all of the power. We're measuring pretty much the total power out of the radar, but out here we're measuring across a range in the spectrum where the energy is distributed out widely. This is a continuum. So out here we're measuring spectrum power density. Spectrum power density instead of measuring total power. So you widen the bandwidth out here, you just get more and more and more power. Widen the bandwidth here at the fundamental, you really don't get much more power because these are 20, 30, 40, 50, 60 dB down out here, and you add these little incremental amounts of power to all that power right there in that fundamental lobe, and you're not getting anything more to speak of. So, in that sense, the assumption that lies behind the RSEC mask as a mask, which is that there exists a spectrum, and it's the spectrum, and we're going to fit it under the mask, is not really an assumption that the laws of physics and nature actually support. And so our problem is to work with that. And so that is the problem that I cite here, where I say radar spectra vary as a function of measurement bandwidth. All right, so this is the problem, and I'm not going to go through the solution, that'll be next week. What I do want to do right now is segue into the lab part of the talk, where I'll actually demonstrate some of these problems for you directly using a radar that we're running out of a vector signal generator. By the way, I apologize for the warmth in here. I turned on the cooler and not getting much airflow. But Katie, how are we doing on the tape?
Good, we got
good.
Like...
Okay, good. So I'm going to move in. I'm going to open the door to get a little more air through here, and we'll segue to the lab part. Are there any questions on what we've done so far? What I've talked about so far in terms of setting up the problem? Yeah, Julie.
Does the Redbook say anything in terms of what bandwidth you should use, like what resolution bandwidth you should use based on the radar parameters?
Good question. The question is, if you didn't hear it, is does the Redbook say what we should use for the measurement bandwidth? And the answer is no. No, it doesn't. But I have written an NTIA report where I said what I think the right bandwidth is to use, and well, not me personally. It's really NTIA says what the right bandwidth is to use, and that report is available on the ITS website, and the title is Radar Spectrum Measurements for Compliance with the Radar Spectrum Engineering Criteria, and it's NTIA TR 05-420, I think. So we wrote a separate report that explains how to do the measurement. The problem, as you point out, is the Redbook says here's what we're trying to fit it to, but it doesn't say how to try to fit it. It doesn't say how to try to do a measurement for that. We had to do that after the fact. All right, we'll First, actually, I will explain this. So, we have two boxes here. The upper box is a spectrum analyzer, and we've used this analyzer for some previous measurements. There's nothing unusual about it compared to other types of spectrum analyzer. The lower box is a vector signal generator, and I've kept it turned off up to this point because it has a cooling fan that makes a loud whine that we can pick up on the tape. But the vector signal generator has been programmed by one of our engineers, Brent Bedford, to produce 1,000 pulses per second with a 1 microsecond pulse width for each pulse. So it replicates this sort of typical medium to long range air traffic control radar, air search radar, and so it has a 0.1% duty cycle. And just to make it easy, we decided to make our radar, in quotes, pulse itself on and off once every second. So this would represent a radar that's rotating really, really fast. And in fact, if you saw real air traffic control radar rotating with a 1 second rotation rate, you'd say, well, something's wrong here because we went through the last talk why that won't work, why you need to scan more slowly with that radar. But okay. So I get this thing up and running here. And it takes just a moment to load the waveform when I power it up. And we'll look. Oh, I need to do one other thing here, actually. Okay, there we go.
The intentions were good.
Okay, good. And then
That's right.
bring in the memory. Okay, and this should take care of it. And now on the spectrum analyzer, we're going to do a clear right. By the way, this is the spectrum that this thing's generating, but I'm going to regenerate it here in just a moment. So, go clear right. And now, we'll bring up our radar at a power level of minus 10 dBm. And, actually I'm going to bring the power level, this is alright, I'll do it this way. Like so. There's a reason I'm doing that. I don't normally turn on 10 dB of attenuation in the spectrum analyzer, but there is a reason for doing that right here, right now, that I'll show you in a moment. Now, this radar is tuned at 3.1 gigahertz, and we're looking across a frequency span down here in the lower right corner of 150 megahertz, and we're seeing the radar pulsing on and off. And the first thing that we see is the problem of this low probability of intercept. This is a radar that has a typical radar duty cycle, and it's actually spinning, if you will, really fast. It's looking in our direction once every second, and yet look, most of the time we see nothing there. Then every so often we see a burst, and I'm going to take some single sweeps here. And I'll try to catch it on one of these. You see how many sweeps we have to take before we get a burst? Here we get a radar burst. Now, what's going on? The radar, well, first of all, the spectrum analyzer is sweeping in frequencies across here, but most of the time the radar is not looking at us. When the radar does look at us, we see a set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 little spikes here in the frequency domain. Sometimes people see this and they say, ooh, it's frequency hopping. No, it's not frequency hopping. This radar is tuned to one single frequency, 3.1 gigahertz. What we're seeing here is the time domain behavior of the radar is being displayed in the frequency domain. In other words, when the radar hit this frequency, when the analyzer hit this frequency right here, the radar emitted the first burst in its little antenna pattern, and that burst was seen as a pulse right here. Then the spectrum analyzer continued to scan for the next millisecond, during which time the radar was simply turned off. We're not seeing anything. Then, when the spectrum analyzer happened to hit that frequency right there, the second pulse in the burst came on, and we saw pulse number 2 right here. And then the radar turned itself off, and then the spectrum analyzer continued to sweep. And then the third pulse in the little antenna pattern burst came on, and we saw that. And so what we see here is the radar's little antenna pattern, if you will, which the way Brent has programmed it has 10 pulses in the main beam and then simply switches itself off just to make it simple. We're not replicating a really tricky, complex antenna pattern. So what we're seeing here are the time domain behavior of the 10 pulses in the radar burst in its main beam, if you will, displayed on a frequency domain display which is intercepting them every millisecond as we sweep across the frequency. So this is one to not get caught on, that if you see some spiky behavior like this coming out of a radar, to think that the radar is frequency hopping. It's probably, some radars do frequency hop, but it's probably not frequency hopping. You're probably seeing the time domain behavior of the radar pulses displayed on the frequency domain display of the spectrum analyzer as it's sweeping in time, because the analyzer has to sweep in time. And we have had cases where we have had people say that they thought that they had frequency hopping radars, and they send us the data, and we look at it and we say, no. Those are the pulses in the radar's beam being displayed in time. But again, we see the problem here is that most of the time when we're sweeping, we intercept nothing out of the radar. And so it takes a long time to fill the spectrum in this way. So we'll continue with what we were doing and go back to the continuous frequency sweeping mode. And so I said, well, wait a minute, we'd like to capture these. Well, here's one quick, easy, and simple way to do it. We'll go over here to the trace function and then go to maximum hold. And you remember that in the maximum hold mode, the spectrum analyzer remembers the highest level that has occurred for any bin that it's measured since you hit that button, and it simply saves it. It just records it, it saves it. Oh, and one thing I should point out at this point is that we're detecting with a positive peak detector. Remember that the positive peak detector latches up to the highest power value that occurs during the time that the spectrum analyzer is sampling every one of the bins on this display, and there are 1,001 bins on this display. So the spectrum analyzer sweeps here 1,000 bins across, and then 1,000 bins again, and 1,000 bins again, over and over. It sweeps 1,000 bins every 100 milliseconds, so it's sweeping 10 bins per millisecond, so it's spending 100 microseconds on each bin. So it looks at that bin for 100 microseconds, then that bin for 100 microseconds, then that bin for 100 microseconds, and it gets through all the bins in 100 milliseconds across here. And the peak detector will latch up to the highest level that occurs in any one of those bins while we're sitting there in this maximum hold sweep mode. Now, we're getting a spectrum formed up here, and this spectrum, trust me, is going to take a long, long time before it fills in completely. We don't want to see all this yellow down underneath. We want every one of these spectrum analyzer bins to be locked up to at some point up in here that actually represents the radar's actual emission on that actual frequency if we're going to look at it for compliance with the RSEC. Admittedly, this is giving us some feel for what the shape of the radar spectrum is, but it's not really giving us, what we want to get. One other thing I want you to note is that the maximum power that we're getting out of the spectrum analyzer, that we're getting out of our little radar here, is, in fact, there we go, minus 10 dBm, which is the power level that I have coming out of the VSG. We're getting minus 10 dBm. Now that's all the power that the VSG has. I've actually programmed it to put out a total of minus 10 dBm of power. And so you notice that although that minus 10 dBm of power is spread across this whole frequency range, we're actually hitting minus 10 dBm right at the fundamental, because these power levels are 10 dB, 20, 30, 40, 50 dB down. Well, 10 dB is a tenth of the power, 20 dB is a hundredth of the power, a thousandth of the power, a 10,000th of the power. So the actual absolute power contribution that we're getting out here in the out-of-band and the unwanted parts, the out-of-band and the spurious parts of the radar emission spectrum is negligible compared to the power at the fundamental, which makes sense because when you're operating a radar, you want almost all your power to be on the radar's fundamental. Ah, there, we finally got it to fill in right there the way we want the whole spectrum to look like. But this takes a long time. Now imagine that instead of a radar looking at you every second, this radar is coming around looking at us every 10 or 12 seconds, or there's a weather radar that has a 1 minute rotation time. You can see how long this could take for a typical radar. So this addresses the low probability of intercept problem for radar emissions. Second problem that we're having here is dynamic range. Remember, we want to get at least 70 dB of dynamic range. We might need to get 90 dB of dynamic range. In NTIA, myself personally, I like to get 100 or 110 dB dynamic range. Well, how much dynamic range do we have here? well, here's the spectrum analyzer noise level right down here. And so how far out of that are we seeing the radar? 10, 20, 30, 40, 50 dB. So we're not even close to being able to get an RSEC compliance measurement on this. But maybe it's not so bad. I have 10 dB of RF attenuation in. So if I take out this 10 dB of RF attenuation, I can drop the noise floor down to there and pick up 10 dB of dynamic range. So now I get 60. So let's in fact do that. We'll go ahead and go to amplitude and then attenuation, 0 dB. All right, and then I'm going to start the process over here. Max hold. There we go. And so now, because I took out the 10 dB of attenuation, the top of the screen is now at a reference level of -10. So this is going to peak out right here at the top, which means that we're almost saturating the spectrum analyzer, but not quite. If we do get saturation, we'll get a little IF overload error indicator over here, which is one of the great things about this particular little spectrum analyzer. And we're not getting that error over here, so that's good. So again, we fill this in, and here's the noise. So we get 10, 20, 30, 40, 50, 60 dB. That's 10 dB shy of what we need for even the minimum RSEC compliance measurement. So here's our dynamic range problem. Now, what could I do here? Well, I could put a low noise amplifier in at the spectrum analyzer's front end, which will drop the noise down maybe another 10 or 20 dB, depending upon what the noise figure of the spectrum analyzer is and how well the amp works. But when I do, I'm going to saturate the spectrum analyzer up here. In other words, I've only got about 60, and on a good day, maybe 70 dB dynamic range out of the spectrum analyzer itself. That's kind of the problem I'm fighting here. And that's not enough dynamic range. What I really, therefore, need to do is somehow measure this part of the spectrum out here with a low noise figure, and then be able to selectively degrade the noise figure or equivalently add attenuation when I'm measuring here near the fundamental. But if I'm sweeping across like this, sweeping across, there's no way for me to selectively change the noise figure and attenuation in this part of the spectrum versus when I'm measuring that part of the spectrum. And so the solution to the problem that we'll go through in the next talk is how we can selectively change noise figure and attenuation in the measurement system to make the system more sensitive with a dynamic range limit that might be about at that level when we're measuring this part of the spectrum, and then change the noise figure and attenuation level in our measurement system front end when we get into the center part of the spectrum where we don't need sensitivity down here. We want to be able to see power coming in up here. So we'll talk about that next time. How can we do that? But you see that you can't do it if you're just sweeping across. If you're simply sweeping across, there's no way to selectively or interactively change noise figure and attenuation as you're going across through the spectrum here. So now I've covered two of the problems. The probability of intercept, which we see is still low. I mean, we still don't have a good fill-in on any part of the spectrum right now, although we are getting a good outline for what we think it might look like. And by the way, if you ever have to take a really quick look at a radar, that's not a bad way to do it. You get a good idea here of what it probably more or less looks like. And we do see the dynamic range problem. We've only got about 60 dB or so, maybe, and I could do some here. In fact, I will do some that'll get me about 70 dB of dynamic range, but still it's not really enough. And at this point, I'm going to actually erase this. Oh, sorry, go back to clear right. Now, look at the bandwidth that I'm using to measure the radar spectrum. 8 megahertz. What did I say the pulse width was? The pulse width is 1 microsecond. 1 over the pulse width, 1 over 1 microsecond is 1 megahertz. I expect that pretty much all the power this radar has to give me, I can get if I measure it in a 1 megahertz bandwidth, and I'll prove that to you. I'm going to go to a span, not of 150 megahertz, although I'll come back to that, so remember it, because I might not. Okay, 0 megahertz span, so we're going to look in time, and I'm going to go to a sweep interval of 1 second, and now we're looking at the radar in time. Span is 0 hertz, so we're looking at a single frequency. The frequency is, the center frequency is 3.1 gigahertz. We're watching time for 1 second, 1 second, 1 second, and every second the radar turns on and then turns itself off. And if this were a real radar, and I'll stop it here, if this were a real radar, we would actually see a whole antenna pattern across here. In fact, next time I do the talk, I'll show you an ASR that will pick up on an antenna. But here we're just making it simple with the vector signal generator, so we gate it on, we gate it off. And inside that little bump right there, here's what's going on. Go back to sweep continuous, and I'll go to actually I'll go, 100 milliseconds. Okay, yeah, that'll be good. 100 milliseconds, sweep time. And now I'm going to go to trigger, video, we'll capture one, I want to capture a different one. Sweeps, actually that's okay. Escape. Okay, there we go. Now I want to capture a little different one. So we'll go to trigger, and we'll give this a little offset. We'll time delay this out by, whoops. That's not bad. Okay. There we go. Okay. Now what I've done is go to a 100 millisecond sweep time, shorter sweep time. So now I can see the details of what's happening inside the radar burst. Again, this replicates roughly the behavior of an antenna when the radar antenna looks right in our direction. And I'll in fact freeze this. There, like so. And if you count, there are 10 pulses in there. So Brent has replicated a typical 10 pulses. And if we count the time between those pulses, we'll find that those 10 pulses are in fact 1 millisecond apart from pulse to pulse. Each pulse is 1 microsecond long. And the power level that we're measuring here is in fact minus 10 dBm. And just in case you don't believe me, I'll add 10 dB of attenuation, like so, and bring the reference level up, and then we'll do this again. Single, all right, there we go. All right, so there we are. There, the reference level top is 0, so we're measuring minus 10 dBm plus just a little bit more. And you know what that little bit of extra is? Just that extra fraction of a dB, that extra half dB, that's a little extra energy off on the sides of that lobe getting in here. But basically, we're measuring minus 10 dBm right there. Now, I'm going to go ahead and save that view, trace to, clear right. Now let's go to a 1 megahertz bandwidth. 1 megahertz is a matched filter. 1 megahertz is equal to 1 over the pulse width. It's equal to 1 over 1 microsecond. So we should still get minus 10 dBm when I measure this in a 1 megahertz bandwidth. And we will go sweep continuous. And I'm going to change the delay on the trigger just a little bit so we can actually see what is going on. Whoop, not there. Trigger delay. There we go. Trigger delay, make it minus 60, and further over. There we go. Okay. And then I'll hit single there. Okay. Here we're measuring virtually minus 10, and that little bit of difference, that little bit of amplitude offset between 1 megahertz, here's the 1 megahertz, between the 1 megahertz measurement and the 8 megahertz measurement, which is yellow, is nothing more than the slightly different amount of power that we're getting in that fundamental lobe when we're in that 1 megahertz bandwidth. Now I'm going to go to a narrower bandwidth. I'm going to go down to 100 kilohertz. So now I'm going to go to bandwidth 100 kilohertz, and we'll go to trace 3, clear right. There we go. Sweep, go, and we'll change our trigger to minus trigger delay here to minus 80. There we go. That's not bad. Okay, sweep continuous, trace 3, clear right. Oh, okay. Yes, I see what happened. It's okay. Bring this down. There we go. Now get it. There we go.
Action.
Action. All right. I did make one little goof here. I want to go back to trace 2, and I want to do trace 2 in a bandwidth of 1 megahertz, which is what I did before, and then go sweep continuous right, and then trigger, bring the trigger back to, what was it, minus 80. There we go. Okay, there we go. Got it. And then back to trace view. Okay, now, okay, so this is important. So remember that we're at the fundamental frequency of the radar. We're tuned right on frequency. The radar puts out 1 microsecond pulses. 1 over 1 microsecond is 1 megahertz. So this measurement was made in a 1 megahertz bandwidth, and once we got to that power level, in that bandwidth, and then we opened the bandwidth all the way up to 8 megahertz, 8 times wider, we only got that much more power in. So we're measuring virtually all the power available in the radar spectrum when we hit 1 megahertz. But if we measure in power in bandwidths that are less than a megahertz wide, then we see the power level drop off at the rate of about 20 log of the bandwidth ratio. And that's because this bandwidth, which is 100 kilohertz for this particular measurement, is only looking at 1/10 of the width at the fundamental that we have in the 1 megahertz bandwidth. So if we can get our measurement up to a bandwidth that equals 1 over the pulse width of the radar, then we're getting pretty much all the power the radar has to give us at the fundamental. And as we open the bandwidth up wider, we don't get any more power, okay? That's important.
Can I ask you a question?
Oh, yeah.
So if you,
Go ahead. Yeah.
You said you can measure with a narrower bandwidth that your noise floor, your system is dropping at 10 log, and then your
Oh, yeah, good
signal's
point.
dropping at 20, so it reduces your
Dynamic range, right.
Is that right?
You're exactly, Randy. What Randy just pointed out was that if, and this is important, that if you're measuring in a bandwidth that's equal to about 1 over the pulse width, we should get the optimum, the maximum, that is, the maximum amount of dynamic range available, because the spectrum analyzer noise varies at a rate of 10 log of the bandwidth, whereas the power that we're measuring here, if we're in a bandwidth that's equal to or less than 1 over the pulse width of the radar, varies as 20 log. They don't vary at the same rate. The radar power is varying at 20 log. The spectrum analyzer noise varies at 10 log. So here we are in the matched filter bandwidth, 1 megahertz, which matches 1 over 1 megahertz. And what's our dynamic range? 10, 20, 30, 40, 50, 60, plus a little, 62, 63. Okay, so 62 or 63 dB of dynamic range. Now we go to a wider bandwidth than that. We don't get any more power at the fundamental, but the spectrum analyzer noise came up at the rate of 10 log of the bandwidth, so now we get 10, 20, 30, 40, 52. So we lost 10 dB of dynamic range by going to a bandwidth that was wider than 1 over the pulse width. Well, that's not good either. Remember, we're looking for 70 or 90 dB anyway, and here we've only got 60, here we've only got 50. Now we come to this bandwidth, 10, 20, 30, 40, 50, 60. So we've lost some dynamic range. Here we've got about 62 or 63, here we've got about 60, and here we've only got 50. So this demonstrates, good point, thank you Randy for pointing that out. This demonstrates that we can maximize our dynamic range if we use a measurement bandwidth that's matched to the pulse width of the radar. We can optimize our dynamic range in the measurement. It's still not enough dynamic range, but at least we're optimizing it. Here, Julie.
I thought you didn't ever want to quite match it. I thought you always wanted to go a little higher. I mean, you were missing a little bit on the top, and I thought that was a standard practice that you...
There are times when you might want to go, yeah, Julie, Julie, come in. Sometimes you might want to go a little wider, or even for that matter, a little narrower. And yeah, you might want to do that. But you'll want to be close to it. You'll want to be close to it. But there are times you might want to be a little off. And in the talk I'll give next week, I'll talk about why you might want to be a little off from that, but not by much. Bob.
So Frank, the delta between your blue and yellow trace there is primarily due to energy in the side lobes of your spectrum?
Here?
Yeah, at
At
the
the
peak.
top.
The peak.
Oh, sorry. Yeah, this is due to the slight difference in the way that the 8 megahertz wide filter is not only getting all the power in the fundamental lobe of that spectrum, but it's getting a little bit of power off in those side lobes off to the two sides. It's not much of a power contribution, but there's a little power contribution, and that little extra power contribution results in that small delta tick right there. Whereas here, we're equal to or possibly even a little less than the width of that lobe. In fact, as Julie points out, if we were to not use 1 megahertz but use 2 megahertz right here for the 1 microsecond pulse width, we'd actually bring that up to about there. We'd get a little extra there. So here we are just technically just a little narrower than that lobe right in there. But yeah, this just has to do with the details of how we convolve the power in the spectrum right there at the fundamental. Looking at at the width of the spectrum versus the width and the shape of the measurement filter that we're using to measure. Oh, and one other thing I should point out. The spectrum analyzer filters are almost the same shape from one filter to the next, but not quite. every spectrum analyzer will have a very slight variation in the shape of the filter as you go from 100 kilohertz to 300 kilohertz to 1 megahertz and so forth on up. You get a very slight change in that shape factor, which again has a little bit of an effect. They do work pretty hard to keep that shape factor almost identical from one filter to the next, but it does vary a little bit, and so again, you'll get a little, there's a little variation there.
What sort of precision are you seeking in these types of measurements?
Ah, good question. What precision are we seeking? A dB, if we can get it. 1.5 dB is probably more realistic in terms of what we can actually get. And remember that the measurement that we're doing is a relative measurement. We're measuring the power in the spectrum relative to the power at the fundamental. So the relative offset is what's important. But we'd like to nevertheless be within about a dB or so. And in fact, for NTIA's purposes, as far as I've ever been concerned, if the spectrum that we're measuring comes within a dB or maybe even 2 dB of the mask, we'll say that it's meeting the mask, because we recognize that we have an uncertainty of a dB, maybe 2 dB in there, and we're not trying to hold someone right in there to that last dB, because we know that we have an uncertainty ourselves, well, we have an uncertainty ourselves of maybe a dB, maybe 2 dB in the measurement that we're making. And so. And usually they either meet it by quite a bit or they don't meet it by a lot. It's usually not a dB. It's usually not a photo finish.
So in this series of measurements, you've decided you're going to dwell right on the center frequency of that radar.
Well, here we are, right. The way I've done this right here, we are. In fact, the preview of next week is I'll show how we actually will stop our measurement on on individual single frequencies, and we'll step our way through and stop sweeping entirely. We'll leave sweeping behind and go to stepping. But Steve, did you have something? Oh, okay. I thought you. Okay. Okay, but remember this too, that at the fundamental 1 megahertz we're getting almost all the power. 8 megahertz we're definitely getting all the power. Right at about minus 10. Right at about minus 10 in here. Okay. Now let's look at the rest of the spectrum. We'll go back to a span of 150. Whoops. Span of 150. Span of 150 megahertz, like so. And I'm going to go to this trace that we made in a 1 megahertz bandwidth, which is cyan. And I'm going to look at the spectrum in that 1 megahertz bandwidth, because that's where we got our optimum dynamic range, and that's about equal to 1 over the pulse width of the radar. So now we go to span of, bandwidth of, it is 1 megahertz, good, okay, set for that. And then we'll go to trace, and I'm going to blank out trace 1 for the moment, which is yellow, and trace 3 for the moment, which is the magenta. And for triggering, we'll go back to free run, and we're going to go to sweep continuous, and we'll make our, we should be running now. Okay, and go ahead and sweep. Not sure why we're not sweeping at the moment. There we go, and sweep. Oh, probably because, there we go. Sorry, trace 2 is blank. Trace 2, clear right, there we go. Okay, now we're good. All right, and sweep time, 1 second, sweep time. Okay.
You have a message at the bottom. That trigger delay in the mode.
That's what mode 0 delay used. Okay. That's fine. Should be fine. Yep, that's grayed out. Well, not sure why we're frozen, but it's fine. We'll just do this real fast. Just walk through it. We'll go center frequency, 3.1 gigahertz. Span is 150 megahertz. Detection is positive peak, and bandwidth is 1 megahertz, and attenuation will be 0 dB. And in fact, actually, I'm going to add 10 dB of attenuation, and the reason is I want people to be able to clearly see that these do hit the same max level. Okay, and now sweep time will be, say, 100 milliseconds, and trace 1 we will blank, trace 2 will clear right, trace 3 will blank again, and we will go to maximum hold trace mode on that. Okay, and we'll fill this in. So this is our 1 megahertz bandwidth measurement, and we'll let this fill itself in for a few seconds. This is our low probability of intercept here. And remember, this radar is rotating, like I said, once every second, so you won't really get this kind of a gift if you're measuring one out in the real world. Although some maritime surface search radars might have a 2-second rotation, and there are some airborne radars that might sector scan back and forth every second.
What about the radars at airports, you know, that look for ground traffic, you know?
Oh, the ground surveillance radars, Bob asked, what about the ground surveillance radars at airports? Those do have a 1-second update rate. So yeah, those are 60 RPM, so they would rotate around as fast.
How about phased arrays?
Phased arrays is a good question. A phased array will not come around and look at you at exact time intervals like every second or every 10 seconds, but here's the key to keep in mind. With any radar, the people who designed the radar want the radar to update itself on any given point in space within some delta t interval, like say every 5 seconds. They don't want the operators to be blind, so even a phased array radar will come back and look in our direction, since we're at a point in space of some sort, will come back and look in our direction within some delta t that the radar itself does not want to exceed. So you still get an update, however you won't get the update every, let's say you won't get an update exactly every 4.5 seconds. You might get an update 3 seconds apart, then another update 3.5, then an update at 4, then 4.5, then back to 3, then 4, then 4.5. It'll vary back and forth a little bit. But they won't let it go 30 seconds without looking in our direction, because that would leave them blind to something that's happening in that direction. But if it is a phased array, you won't get the deterministic update that you get with a rotating array. Instead, you'll get a little more random update. But you'll still have a delta t within which it will come back to update you. Okay, so here's our 1 megahertz spectrum. And we will hit view, okay, which view here freezes that display, 1 megahertz down here. Now, let's go to the trace display, and we'll go to trace 1, and now we'll make our measurement in, well, let's just pick a number a little bigger than 3 megahertz, a little bigger than 1 megahertz. We'll pick a bandwidth here, which will be 3 megahertz, just a little wider bandwidth, all right, and now we will go back to trace 1, yellow trace, clear right, max hold, okay, and away we go. Now, what's happening, we can see this right off the bat, is we've got about a 10 dB difference out here in the out of band and the spurious part of the spectrum. This is the unwanted spectrum out here. 10 dB offset. We're getting 10 dB more power out here, and that's 20 log of the ratio of 3 megahertz to 1 megahertz. So that's just what it ought to be theoretically. In fact, I'm almost surprised it's so good. But here's the problem. Up here at the fundamental, what power level are we going to measure in 3 megahertz? Minus 10. So where, and sure enough, there it is. See, it's peaking out right at minus 10 right there. I'll just let it fill in just a bit more, and then I'll come to it. So here's the problem. People say that they want to know that this radar fits under that mask, which comes out like this, drops down 40 dB, and then rolls down like that, and then has the ultimate suppression level. But if we measure in 1 bandwidth, I get a suppression level at, let's pick a frequency. Let's pick this frequency right here. In this bandwidth of 1 megahertz, I get a level over here, which is at 10, 20, 30, 40, 50, 60 dB down. That level's 60 dB down right there. And on that same frequency, in another bandwidth, that level is only, oh, sorry, I misspoke. Go from here, yeah. 10, 20, 30, 40, 50. Okay, at that frequency right there, in the 1 megahertz bandwidth, the emissions are 50 dB down, and in this second bandwidth of 3 megahertz, the emissions are only 40 dB down. So you don't get a fixed amount of delta between a power level that you measure at a frequency in the spurious spectrum versus the power at the fundamental. And this is a problem when you have a mask that says you're supposed to be so many dB down and you're so many megahertz out. The answer to that is a question, which is, in what bandwidth? And we're not doing anything, wrong here. So I'll leave you with that sort of until next time. But I will do one other measurement here. Having gotten this measurement, I'll freeze this one. Freeze it. Trace 1. Okay, we go to view. Okay, now I'm going to trace 3 right here. And trace 3, I'm going to go to a 300 kilohertz bandwidth. So go bandwidth, 300 kilohertz. Kilohertz right here. And now we go to trace 3, clear right, max hold, and away we go. Now in this more narrow bandwidth, it's even more problematic. So by the way, in my yellow, blue, yellow, cyan, magenta traces, I'm to some extent replicating the bandwidths that I used when I was looking at the power at the center frequency. Earlier I used 8 megahertz for the yellow. Here I use 3 megahertz, but it's the same concept. Now when we look at this, and we'll let the magenta fill itself in a bit. In fact, I'm going to turn off. I'm going to blank that display. Okay. So now we have 1 megahertz in cyan. We have 300 kilohertz in magenta. And I'm going to momentarily, in fact, blank out the 1 megahertz data. Okay, so here is our data in 300 kilohertz. It's going to take a little while to fill this in, but be patient. Eventually, if we wait long enough, this will, no, actually this will not. This will go down at 20 log of the bandwidth ratio. Okay, in a 1 megahertz bandwidth, we saw minus 10 dBm. If we go to wider bandwidths, we don't get any more power, but as we reduce the bandwidth, we do go down at 20 log of the bandwidth ratio. 300 kilohertz versus 1 megahertz is a factor of a third, and 10 log of a third is going to be 10 log of, 10 times 0.5, sorry, 20 log. Back up. 20 log of 1/3 is 20 times 0.5, which is 10 dB. So we should see 10 dB less power here than we did in 1 megahertz. And in 1 megahertz, we saw power at minus 10. Here, we should see power at minus 20. And in fact, I'll bring the marker over. We're about minus 18. So we're pretty close to theory there. Okay, so we lost 10 dB of power. We lost 10 dB of power here. And on our noise on the spectrum analyzer, we went down at 10 log of the bandwidth ratio. So we went down 5 dB on noise power here versus 20 log, which was 10 dB on power here. So this dropped 10, that dropped 5. So overall, we lost 5 dB of dynamic range by going to the more narrow bandwidth. By going to a bandwidth that was less than 1 over the pulse width. This goes down at 20 log. This noise goes down at a mere 10 log, half the rate in decibels, and so the difference between the two is 10 log. So we lost 10 log of bandwidth ratio. We lost 5 dB of dynamic range, but there is some good news. There is a little bit of good news here, and I'll let this kind of. Actually, this isn't too bad. I'll leave that the way it is right now.
It's a nice colored trace.
It is. Don't you just love magenta?
I do.
I like a nice magenta. I wish we had chartreuse, but at least we've got magenta. Now I'm gonna bring back trace 2, which is the 1 megahertz data, and trace 2 clear right. No, not clear right. Trace 2 view. Oh my God! Don't do that. Okay, here we go. Trace 2 view. This is the 1 megahertz data. Looks like this. Now this is kind of nice. Here's something kind of nifty. Right here, it's a little hard to see, we've got our 10 dB offset right here in power level. That's our 20 log offset. And look what happens out here. We're still getting a 20 log offset out here, like right here on this frequency, from the cyan 1 megahertz to the magenta 300 kilohertz. It's not quite 10 dB, it's probably about 8 dB right there. But all in all, if we go across, like say right here, there's the power level in 1 megahertz, and if we come down 10 dB, there's the power level in 300 kilohertz. So here, the entire spectrum from here to here shifted itself from these power levels down 10 dB to these power levels, but the relative amplitude between a power level measured here and a power level measured here now is a fixed offset. It's a fixed offset. If I draw this curve and I add 10 dB to the magenta curve, I can slide the whole thing up 10 dB and it'll overlap exactly. Oh, at least now we've found a place to anchor our boat in the tossing spectrum ocean. If we measure the spectrum in a bandwidth that is either equal to 1 over the pulse width, like we have here with the cyan trace, or less, we can replicate the spectrum shape, and the mask, remember, gets drawn starting at the power that we measure at the fundamental. So for the 300 kilohertz measurement, we would put the top of the mask right there. For the 1 megahertz measurement, we put the top of the mask here, but then we draw the mask down from there. So if we want to check compliance with the mask, operationally or functionally speaking, we can at least get consistent results from one spectrum to the next in terms of how they fit the mask by measuring the bandwidth that's equal to or less than 1 over the pulse width, but not greater than 1 over the pulse width. Because if we go greater than 1 over the pulse width, now what happens is as we will recall, is, and I'll freeze, or I'll just bring it back. We come back here to the yellow, and we go view. Here's our measurement in 3 megahertz. Because remember, now if we go to this wider band of 3 megahertz, we don't get any more power here, but these levels just keep coming up. So my joke is that I can make any radar fail the RSIC by measuring it in too wide a bandwidth. But, Julie, to go back to your comment earlier, the Redbook does not say anything about a bandwidth in the measurement. The Redbook assumption is that there's a mask in the radar, either it fits it or not. So the NTIA report that you can download online about how to measure radar emissions for compliance with the RSIC does address this issue, and there's a table that shows you for a given type of radar emission how to pick your bandwidth. I've been talking about simple radars where just pulsing on and off. They're more complex radars, but the problem and the solution remain the same. If we measure in too wide a bandwidth, we can eventually just simply make the radar fail the mask. If we measure in a wide enough bandwidth. But if we measure in a more narrow bandwidth, we can at least get a set of consistent spectrum results we can fit under the mask. This may or may not have been exactly what people had in mind when they designed the mask, but at least operationally speaking, this is a way to deal with it. Now, we still have to cope with the fact that we're not getting enough dynamic range here, and the fact that this spectrum measurement is taking just literally forever to complete. I mean, look at this spectrum. I think trace number 3 is still running, and we're still not even close. Let's go to trace 3 here. Yeah, trace 3 is still active, still running max. Well, look, I mean, it's not even coming close here. So in the talk next week, we'll talk about how we get the dynamic range and how we can efficiently work our way through the spectrum. There's still times when it's about as exciting as watching grass grow, but it's a lot more efficient than this.
This is pretty cool stuff.
And that concludes today's talk with the problem of measuring radar spectrum. Any questions? Okay, 90 minutes. We're right on.